prove that the volume of a sphere is V equals 4 over 3 pi r cubed. And when you have this kind of proof, it is easier. Now, what we have to do is to name our Cartesian plane as y and x. So after naming this, then the first thing we have to do is to estimate a semicircle here, and this semicircle moves like that. And after estimating this, assuming we make a rotation of this semicircle in that direction, it will form a sphere. My diagram is not accurate. This is not a perfect sphere. It looks like an oval, but don't worry about that. So let's make an estimation of the small strip that has been made a rotation to this side here, and it will form a smaller disk. So this disk here had a small distance delta x, and the center is from here running to this point with a certain radius. Now we can call this radius y because it is along y coordinate. This is parallel to y axis here. So therefore, we also know that if we consider a cycle, then the equation of a cycle running from this 0 as the center, and then this one is given by x square plus y square equals r square, where r is the radius of this cycle form. But for now, we have a sphere, and of course in these two dimensions it looks like a cycle. So now, since our radius here is in terms of y, then we need to make y the subject here, and we have y as r square minus x square. But of course, y is squared, so for us to remove the square, we need to get the square root on both sides. Therefore, y equals to the square root of r square minus x square. We can move on and get the volume of this small disk. Remember, if we pull out this small disk and we draw it out, it may look like this. That is our small disk. It is in form of a small cylinder with a base, and this base is circular, and we have a radius, and this radius is in terms of what we get here. We set is y, and y is in form of that. Now, this small thickness is what we have here, and that is delta x. So for that case, we can now move on and be able to get the volume here. And since it is a small volume, then for small volume, we also have delta V is given by, now we have one, assuming we have drawn very many of these small disks from negative r to positive r, making the total volume of this sphere. Then for one, that is the same as the volume of this small cylinder. And since there are many, we need to have the summation of all small disks that we have formed. Therefore, we can estimate using a sigma notation where our small radius is estimated from I up to infinity, since our cutting may be small and very many of them obtained. And I also ranges from 0 up to infinity. So for that case, we will estimate one of this disk, its volume. From this diagram, we have area of the base is pi r square times the height to make its volume h. And remember, this h here, according to our diagram here, is delta x. So let's go on and make substitution. Therefore, delta v is given by the summation of r ranging from I up to infinity of pi, and instead of writing r, remember r, yes, the radius was y, and we know our y was square root of r square minus x square, and h is delta x. So from here, we can now make this to the whole volume of the sphere by integration. So we can integrate the left-hand side, and delta v changes to dv equals, the integral sign will replace this sigma notation, and we are moving from 0 up to r. Therefore, we have here pi, and this is multiplied by also r square minus x square with respect to x. Now, before we proceed, let us move on and make a small analysis here. Of course, there are two ways in which we can make this integration. For now, what I've just given here is a short form where I'll have a hemisphere here to be able to estimate the volume of this hemisphere. We can integrate from 0 up to r. But if we need a long form integration, we will start from negative r to r to get a full volume. What I've just done here is volume of hemisphere, and our main interest is to get the volume of this whole sphere. And for us to be able to get the volume of this sphere, then we can double this hemisphere from the positive side by 2, meaning it's like we are multiplying the whole thing here by 2 also. So if you need me to make this estimation from negative r to r, write a comment in the comment section, then I'll make a special video for you, and you'll see that the results will be the same. So therefore, we'll have also here. And since pi is a constant, then we can pull it out. But remember, r was squared, therefore we also need to square this as well. I think let's make the same square here, since from our formula here, r is squared. So the same square applies to all values for the radius. The integral of 1 with respect to v from the left-hand side yields v. Then we'll collect all the constants together, and that is 2 pi, and we'll have integral from 0 to r. Since there are the 2, then this is the total volume of our sphere. And therefore, you can see here that this square root will cancel with the square here, and we'll have what is left here is only r square minus x square with respect to x. Now here this r is not x, therefore is behaving like a constant. So integrating a constant is simply we attach the variable in which we are integrating with respect to. So let's do that and make our integration. So we have twice pi, and since it is a definite integral, then we need a square bracket here, and the first part here we have r square and multiplied by our x minus. So the integral of x square is like raising the power by 1 from 2 to 3 and divided by our new power, and that is 3. Then from the lower limit 0 to upper limit r. Therefore, we'll go ahead and make substitution of x with r, and we can rewrite what is here 2 pi. We'll have here our r square times the value for r minus r cubed all over 3, and we also substitute 0 to x, subtracting it away. And since we have x in all these parameters, then substituting 0 will make this vanishes to 0. So it's useless for us to put that. Therefore, let's go on and continue to simplify our work here. And we have v equals 2 pi, and this is multiplied by r squared times r, we get r cubed. Now we can put this over 1 because this side here we have fractions, so we have here r cubed also over 3. And then we can make this subtraction simple, so we can move on and multiply this by 3, the numerator and denominator, to obtain the same denominator, that is 3. Therefore, we have our 2 pi. Inside this bracket still we have 3, r cube, and 1 times 3 is also 3 minus r cube over 3. Now here, since the denominators are the same, we subtract the numerators, maintaining still our constant outside here, that is 2 pi, and this is multiplied by 3r cube minus r cube, we get 2r cube. Then this is over 3. And to make it look simpler, we can also put this one over 1. Then multiplying the numerators separately, 2 times 2, we get 4, and times pi, we also get pi r cube. Therefore, v equals 4 pi r cube, and 1 times 3 is 3. So normally we place it where the number is, and we have 4 over 3 pi r cube as the question suggested for us up here. And of course, we have just proved here that the volume of a given sphere is given by v equals to 4 over 3 pi r cube. If you have gotten this video helpful, please also support this channel by subscribing to the channel. Like this video and share with your friends, and see you in our next upcoming videos.